All right. First thing I'll say is, remember last class there was a question. Sorry, I forgot your name, sir. Colin asked the question about, remember this series and whether or not you could split up. Did you see I put a video out? If you go to YouTube, I put a video on our channel that explains why that doesn't work. So it doesn't work. You can't. Yeah, it'll show it, and so you can take a look at it. So this quiz, it's weird. I give this quiz every single semester, same quiz every time. And I usually do it right after I cover geometric series and all that stuff. And it's amazing that it stumps so many students. This is the most basic test we have for series. This is it. And so every series, almost every series should start with this test when you're trying to figure out what it does. All I was looking for is this. Well, what is the nth term test? You have to know that, which means that all you're doing is you're taking the limit as n goes to infinity of the sequence of what's inside there. Just take whatever's in the series, whatever's in the sum, and tell me what happens when n goes to infinity. If that does not go to 0, if it doesn't go to 0, like it goes to some number like 2 or 1/2 or -1, anything other than 0, it tells you that what? This means the series diverges. So, for example, if that goes to 1, then it's basically saying that all your terms are becoming 1 or close to 1. So it's 1 plus 1 plus 1 plus 1 plus 1. That gets infinitely large. It diverges. And that would work for any number. It goes, even if it goes to 0.1. 0.1 plus 0.1 plus 0.1 forever would be divergent. Now, it also says that if the limit as n goes to infinity of this equals 0, that what? What is that? We know if it doesn't go to 0, it diverges. If it does go to 0, what does this test tell you? Nothing. Nothing. The test fails, okay? And that's one of the biggest mistakes that I see students make. They say, oh, okay, if the inside goes to 0, it converges. If that were the case, series would be easy, because you would take the limit inside and it would either go to a number or it wouldn't. It would go to 0 or to something other than 0, and you'd always be able to tell me converge or diverge. Always. The problem is that when it goes to 0, it's not enough information for us to determine either way. Okay, that's the nth term test. Any questions on that? Sure? Now, I have a handout for you today. If you're coming in late, you missed the quiz, and I'm not going to give you a redo on it. Y'all need to be on time. I can't have people, half the class walking in here 5-10 minutes late. Here we go. If you had a car breakdown or something today, that's one thing, but you can talk to me. Okay. So this is going to be, I'll let everyone get this. We good? Just leave them over there. Okay, so this is a summary of the convergence and divergence tests for series. You are allowed to have this on your test, right? So along with your other formula sheets, this is allowed. Now don't go throwing a bunch of other stuff on the back of it. That's not allowed. This sheet, as it sits in your hand, is what you can have. The first test on this summary here is the nth term test, right? So that's what we're looking at right now. If you read this across, you're looking at the series. Now, they use this notation, and you'll see me use this also. A lot of times, you'll just put the sigma in the a sub n, and it's understood that it's an infinite series, that n starts at 1 and goes to infinity. It just cuts down on the time, so it's kind of a shorthand, all right? So that it says that if you have a series that looks like that, then it diverges if that limit goes to something other than 0. That's what I just said. And then in the comments column, it says it's inconclusive if it does go to 0. So the test fails. All right? Now, I stole this from someone online. They didn't have it copyright or anything like that. I just want you to know I did not put this table together. There's like, you just search summary of convergence tests and you'll get like hundreds of hits. So I took this one and I just added a couple of things into it, which we'll get to. We are going to, well, look at the next one, geometric series. We covered that last time, right? And notice that the geometric series, it starts at n equals 1 and goes to infinity, and then it says a r to the n minus 1. That's the first version I gave you, isn't it? And then I showed you last class that you could actually start at n equals 0 and the formula changes a little bit. So that's the one that's on this formula sheet. And it gives you the conditions for convergence. Absolute value of r has to be less than 1. Divergence if absolute value of r is greater than or equal to 1. So we did that already, right? Now today, my goal is to cover p-series, integral, and comparison tests. And then next class, ratio, root, alternating, and absolute value at the very end. Now the last one, you can see I wrote that in by hand. That one is, it's not really a test, but I wanted to have something on here that reminded you of those telescopic or collapsing series, because there's really not, remember when we did those in class, we didn't do a test, we just wrote them out. And look in the comments, I said, find S sub n and determine a cancel pattern. So you have to figure out how things are canceling, and then take the limit of that expression as n goes to infinity. So that's everything. Let's start, going through these now, p-series, integral, test, comparison. All right? Another thing I have to mention to you before we continue or proceed today, there's some properties of series that I did not put up on the board that I'd like to point out that are in the book. And they are on page 441. On page 441, it's theorem 8 on that page. And it answers a lot of questions that I've been getting from students who have been really trying on their homework. What you can and can't do with series. So this theorem, I'll just kind of shorthand it up here. It says, suppose that you have two series, a sub n and b sub n. All right, so those are two separate series, right? Suppose these series both converge. All right? They both converge. What does that mean? They add up to some number, right? They don't go to infinity, they don't diverge. If they both converge, then this is true. What is this saying? You can pull a constant out of the series, all right? I know my sigmas look crazy right now, but it's because it's all in your book, all right? That doesn't even look like a sigma, actually. Okay? So that means a constant can come out. As long as that series converges, that's okay. The other one is that sum a sub n plus or minus b sub n equals sum a sub n plus or minus sum b sub n. Now that in the book they do those as two separate properties. I'm just putting them up together. This one says that if this guy converges and this guy converges, right, and you add them, it's the same as doing them individually. So let's say this is geometric and that's geometric and they both converge. Then all you have to do is look at them separately, figure out what they add up to, right, what the geometric sum is, and then add those two answers. If you subtract, you subtract. But the big key here is that they have to converge. So let me show you an example of where this theorem would not work, because I think most people want to apply this theorem all the time, and it just doesn't work this way. Let's say you have something like this. Sum 1 over n minus 1 over n plus 1. Does that equal sum 1 over n minus sum 1 over n plus 1? Shaking your head, no. Why not? This is harmonic. 1 over n is harmonic, right? 1 over n plus 1 is also harmonic, because it just goes up by 1, right? You start out, it's like you plug in 1, you get 1/2, then 1/3, 1/4, 1/5, 1/6, 1/7. And we showed that that was harmonic and it diverged last time. So they're both harmonic, right? They're both divergent. So if you come over here and try and do these, those are both divergent. Those both go to infinity. What's infinity minus infinity? We don't know, right? But if you actually write this out, this is telescopic, and it converges to something. So if you were to actually write out, let's write out the nth partial sum of this, S sub n. Wouldn't that be, what do I get when I plug in when I plug in 1? 1 minus 1/2, and then the next one would be plus what? 1/2 minus 1/3 plus, and we keep doing that, right? And at the very end, we'd have like 1 over n, and then 1 minus 1 over n plus 1. And look what happens all in the middle, right? Cancel, this cancel, this cancel. Everything would cancel except what? First and last. And then what you do is you take the limit as n goes to infinity of S sub n, which is the limit as n goes to infinity of what was left? 1 minus 1 over n plus 1. That's that first and last one. As n goes to infinity there, you're left with what? 1. 1 minus 0, which is 1. So that series actually converges. Do you see why you can't, if individually they're divergent, you can't split them up. But if individually they were convergent, you could. Does that make sense or not? Yeah? All right, so don't just start ripping sums apart or series. Don't just start splitting it into series, multiple series, unless you know for a fact that each piece converged. All right, I'm ready, I think, to start today's stuff. Are y'all ready? Y'all seem worn down. How many more weeks we got? What are we down to? 4? Is it really? What do we have? We have this week, so 1, 2, 3, 4, 5, 6, 7. That's a holiday. 8, 9 classes. I believe that's 9. When are our finals? I think our finals are the week of the 9th through 13th. Yeah, so I think we have 9 classes left. We're going to have a test after Chapter 8. It'll be all Chapter 8. Here we go. So we have now today the integral test. I think that the integral test is pretty intuitive, meaning that most students have a pretty good, I guess they can wrap their heads around the idea pretty easily. See, what we're doing is we're trying to look at a series, right? And seeing if these things add up. So we're looking at something like a sub n, that's a1 plus a2 forever. And we're asking ourselves, does this converge, right? Does that go to a number or not? Now, we know that if we graph, remember when we were graphing the sequence? Remember when we graphed the sequence? We would plug in 1, and that would give us our first term. And you know, it might do all sorts of things. Like this is our a sub 1. And then, you know, we plug in 2, and, you know, it might do this and do that and do this. And it would be dots everywhere, right? Yes? If I look at this dot, a sub 1, and I make a rectangle out of it like this, what's the area of that rectangle? How tall is it? A sub 1. How wide is it? 1, right? So what's the area of it? 1 times a sub 1 is a sub 1, isn't it? So the area of that rectangle is a sub 1. Now, if I do this rectangle here, what's the area of that rectangle if it's a sub 2 high? If that's it's a sub 2. Because again, the width is what? 1. And I could keep doing this, right? And keep doing the next one, and that area would be a sub 3 and then a sub 4, and so on and so forth, right? So if I could add up all those areas, I would know the sum, wouldn't I? If I could add the areas up. Agreed? But if we look at the series or the sequence of points as a function, then this would almost be like an integral, wouldn't it? Like the area underneath a curve. See, we don't have a curve, though. We have a bunch of dots. So this is where the integral test is kind of born from. The idea of, hey, we're still looking at areas. So before we can apply the integral test, we have to have some conditions that are met. So if you look on your sheet that I gave you, please look on the integral test and just look at the right side. Well, you know what? Don't look at that yet. Just keep it out. Integral test. Let me write down the conditions first, all right? So here's the integral test. Suppose that a sub n is positive, decreasing, I should say positive and decreasing on, and let's just say, that's good. Just positive and decreasing. So what does that mean? We have a sequence that's what? Positive means above the x-axis, right? Basically, every time you plug in n equals 1, 2, 3, it's always a positive number, right? Decreasing means that as I move from left to right, what happens? It goes down, right? Goes down. So our sequence has to be doing that in order for us to use the integral test. Now, I'm going to put a little side note next to decreasing here. I'm going to put eventually. Because decreasing, we don't mean strictly always decreasing. What we mean is that as I move to the right, my sequence might jump up and down and up again and then down, but eventually it starts going down and down and down forever, all right, and never comes back up. So at the beginning it might do something weird, but eventually starts to taper off, all right? Okay, if that's true, if our sequence does that, we will let f of n be equal to a sub n. In other words, we're just going to take our sequence and look at it as a function. And we have done this before, all right? We did this in the very beginning when we were studying sequences. We're going to let f be defined as the function of real variables or real numbers instead of just at 1, 2, 3, 4, 5, 6, 7, 8 forever. Then if f is continuous, on 1 infinity and readily integrable, then we have the following. So let's just talk about what that is saying. We're basically we're treating our sequence as a function of numbers, all numbers, instead of just the integers. If that function is continuous, which means you can draw it without picking up your pencil, basically, right? And it's readily integrable, which means we'll be able to find the antiderivative of it. Then here, the following things are true. Okay, here are the things that are true. 1, if the integral from 1 to infinity of f of x dx converges, then the series converges. So whatever the integral does, right? Well, I should say after the second property, but right now, if the integral converges, so if the integral goes to a number, so does our series. Our series converges to a number. And then the second part says, if the integral diverges, what do you think? Yep. The series diverges. Couple of notes here to realize. Note what we need: f continuous, f decreasing, f greater than 0. You need not start at 1 and f eventually decreases. So I'm kind of stating some of the things from before. See, if the sequence is always positive, then the function needs to always be positive also. That's what that last thing says. If the sequence is decreasing eventually, then the function should decrease eventually, and then f must be continuous. All right? So let me try and put a picture to what's happening here, right? Just so we can all agree that this is true. So let me draw a sequence which decreases eventually. So here's my sequence. Maybe it starts here, maybe it goes up, comes back down, maybe it goes back up, and then at that point, from there on, it starts decreasing. And I'm going to make it go to 0, okay? Like that. Now I could come in here with rectangles, right? Like this. Agreed? Now, if there is a function that represents that sequence, but over all numbers, instead of just the integers, my function would be going like this. And then look at what happens here towards the end. So can you see that if underneath the red, if the area, and we have to be looking only, we don't look over here, right? Because this is 0 to 1. We're only going from 1 out. If the area under the red is finite, right, goes to a number, then our sequence also must go to a number. Do you see? Because at the end, aren't all my rectangles below, right? See that? So whatever the red does, if it converges, then so does my sum of my rectangles. And remember, my rectangles, those were A1 plus A2 because the area, right, was the height, and then the width was always 1. Do y'all follow this? And then if that red blows up and goes to infinity, so that means that my area of my rectangles had to go there also. Now don't confuse this with Riemann sums. We're not cutting this into an infinite number. I'm not cutting these rectangles in an infinite number. I'm just adding them up. And I'm saying, well, hey, look, you know, it's connected to that integral also. So do you buy the test at least, that it's going to work for us? All right, let's see how we can apply it. So let's do an example. Here we go. The question is, does this converge or diverge? Sum n equals 1 to infinity of n over n squared plus 4, and that's it. All right, real quick, the first thing I'm going to do is the nth term test. Nth term test. So that means I'm going to take the limit, right? As n goes to infinity of what? Of the sequence inside, which would be n over n squared plus 4. If I take that limit, what do I get? Infinity over infinity, right? So apply L'Hopital's rule one time. One over 2n. Now let n go to infinity and you get what? 0. What does that tell me? Nothing, right? That tells me I don't know that the nth term test failed, right? That's what this says. Nth term test failed. Inconclusive. So it's kind of like, oh well, maybe we would have got lucky, it would have gone to 1, we would have been done with the problem, right? But it didn't. So now we have to try something else. Well, is it a geometric series? What was the pattern of geometric? There's something about geometric you should always realize. The power, right? The index variable, n, is a power in a geometric series. Here, our n is not a power on anything, right? N is just the base. So it's definitely not geometric, right? So it's not geometric, can't do that. The only other thing we talked about was what? Harmonic? Harmonic? Well, harmonic, didn't we have to have just n in the bottom? We have an n squared. That's not harmonic. Is it telescopic? Well, telescopic had to have something minus something so they would start wiping each other out, right? I don't see any way we're going to be able to rewrite that as something minus something. Could you do partial fractions on that? Can you factor n squared plus 4? No, so you can't split into two factors. The best you could do is try and rewrite that as like an irreducible quadratic. And remember when we did this where we said anytime we have an irreducible quadratic, we put an ax plus b on top? If you did this, you would get back the n. You would just get n over that again. It would be the same expression. So there's no way to get this partial fractions to decompose. So we're stuck. Well, maybe the integral test will work. Maybe. But we have to have some conditions be met. So the first thing I'm going to do to see integral test, if it works, I'm writing this down. Integral test. Here we come. I'm going to let f of n be equal to a sub n, which is n over n squared plus 1. What are the things I have to have in order to be able to use the integral test? It has to be decreasing, has to be continuous, and has to be positive. Well, let's check the easiest ones first. Is it continuous? Is f continuous? Plus 4, thank you. Is it continuous? Well, that's a polynomial divided by a polynomial, isn't it? And there's no division by 0 ever? So it's a continuous function. Yes. And you could put here poly over poly or something like that if you wanted to really convince me you knew what you were talking about. And then, is it positive? Is f greater than 0? Why? If I take this and ask you, is that greater than 0, right? You can multiply both sides by the denominator. Agreed? And you would get n is greater than 0. Do I have to worry about flipping over the inequality? Why not? When I multiply both sides by n squared plus 4, why do I not have to worry about flipping the inequality? N squared plus 4 is always positive, isn't it? So it's never going to, right? If I multiply both sides of the inequality by a negative, I have to flip it over, which would change. I would say n is less than 0, wouldn't it? But that doesn't happen. So that's not just one of those things like, oh, who cares? That's a subtlety that you have to make sure you're paying attention to. So I multiply across, I get n is greater than 0. Is that true? Well, yes, because where are we going to be looking? From 1 out, right? So this is true. So I know that I'm getting positive terms out. I know it's a continuous function. The last thing I need to know is whether or not it's what? Decreasing. Now here's where things get tricky. Because you're not looking at it as a sequence anymore. Okay, these are not dots. F is a function defined on 1 to infinity and everything in there. That means 1, that means pi, that means everything, right? I need you to show me that that's decreasing. How do you show that a function's decreasing? That's a drum roll. Graph it, yeah. That's one way. But see, it's not a sequence, though. We can't look at terms. Cal 1. Cal 1. How do you know if a function is going up or down? It's connected. How do you know if a function is going up or down? No. No. Okay, look at a function that does this versus a function that does this. What's the main difference? I mean, the one on top's increasing, the one on the bottom's decreasing. Take the derivative, find the slope. Exactly. Doesn't the slope of the tangent line tell you if you're going up or down? Remember, if the derivative is positive, you're going up, right? If the derivative is negative, you're going down. Yes? Derivative tells you what your function is doing, up or down. So to figure out if f is decreasing, what we actually have to do is this. We have to show that the derivative of that function is less than 0. Less than 0 means negative. We need to show that that derivative is always pointing down. Now, I'm going to put next to this, eventually. Because it may not point down initially. It may go up a little bit, but eventually it needs to come back down. So integral test requires you to actually have to take a derivative. So let's take the derivative of f. Not L'Hopital's rule, derivative, the true derivative. What's the derivative of this function? So it's up there, isn't it? It's quotient rule, right? Derivative of the top, 1 times the bottom, n squared plus 4, minus the derivative of the bottom, 2n times the top, and all over the bottom squared. Well, L'Hopital doesn't tell you what the derivative. L'Hopital tells you what's happening as n goes to infinity. We're not looking at n goes to infinity here. We're saying what's the slope of the tangent line. Questions? Let's clean up the top. We get what? N squared plus 4 minus 2n squared, which is really n squared, negative n squared, right? Can I write it this way? 4 minus n squared? Is that all right? Over n squared plus 4 squared. What's my question again? Is this negative? Yes or no? Is that negative or not? Convince me it's negative. Why? Okay, multiply everything by the denominator. That's fine. You get 4 minus n squared is less than 0. I agree with that. Now what? Can I add n squared to both sides? Is n squared always bigger than 4? Is n squared always bigger than 4? If it's 1, it won't work, right? If it's 2, it won't work. But 3 on, right? Actually, anything after 2 will work, right? Anything after 2. That's going to be true, isn't it? And remember I said that eventually we need to decrease? This is what I'm saying. Look, if this is true, if n is greater than 2. Do you agree with that? So what happens is that my derivative is not negative until I get to 2. Once I get to 2, it's negative. And I can promise you it's going to stay negative the rest of the way, which means my function is going to be decreasing after 2. So it's eventually decreasing. Follow this? You have to show all this on it. You know, if you're going to use the integral test, everything here has to be confirmed before you do the test. Next step. Have we shown everything? It's continuous, it's positive, it's decreasing, right? Those are the things we need to show. So now, let's integrate it and see if it converges or diverges. So here we go. We're going to integrate, and we're going to go from 1 to infinity. So we don't care about that, the fact that it didn't decrease right away. We don't care about that. We're still going to go from 1 to infinity, and we're going to integrate the function. Now, in the formula, this is where they switch to x, which is fine, instead of n's, because we've never differentiated with respect to n, or integrated. So I'm going to make this x over x squared plus 4 dx. That's the same thing, right? X instead of n's. What is the antiderivative of that? Well, this is a basic substitution. du is 2x dx. We're off by a half. Does everyone see this is a basic substitution? This integral becomes 1/2 integral 1 over u du. Using that basic substitution. What's the antiderivative of 1 over u? Natural log. So this is 1/2 natural log u plus a constant, right? However, I have a definite integral. So this becomes 1/2 natural log. What was u? X squared plus 4. And I'm going to evaluate that where? 1 to infinity. So plug infinity in first. Infinity squared plus 4 is infinity. Natural log of infinity is infinity. Half of infinity is infinity. So you're getting infinity. Am I done? Can I say diverges right now? No, because what if it's infinity minus infinity? Then I'll have L'Hopital in there. So I need to check what happens when I plug in 1. What do you get when you plug in 1? 1/2 natural log of 5. That's a number, isn't it? Constant. Infinity minus a constant? Infinity. It diverges. Right? It diverges because it goes to infinity. And what that means for us is what? Finally, we've come to the result. Therefore, sum n equals 1 to infinity of n over n squared plus 4 diverges. It's a lot of work, isn't it? do y'all think, though? I mean, well, I mean, ugh, yeah, could be. You got to start getting quick with these tests. The issue is going to be, again, the same thing it was when we had integration, when we were doing the techniques of integration, and that when you're faced with an integral, you didn't know what technique to use necessarily, right? Same thing's going to happen with these series. You're going to have a series, and you're going to have basically all of these tests to use, and you don't really know which one exactly will work. And the only way to get good and quick with it is to do as many problems as you can. And if you're doing the problems in the book and you run out and you want more, I've got plenty more problems for you to try. But you have to be doing these. Don't expect to come in here, watch me do 3 or 4 examples in class and be like, oh, I got it. I assure you that won't work. All right, let's try another example. Sum n equals 2 to infinity, 1 over n natural log n squared. Let's do a quick nth term. What's the limit as n goes to infinity of that? 0, right? And what does that tell me? Inconclusive, right? What do you think I'd do if you do that and you put converges on a test? I give you no credit. Right? And that's what you agree that's what you would deserve? There's no credit on that? That's the whole point, is that if it goes to 0, you don't know anything. But if it didn't, it saves you all this time that you might go through all this integral test. And if you would have just done nth term in the beginning, you would have saw that it, worked out. So you always want to run that test first. Everyone understands why that's 0, though, right? Denominator goes to infinity, 1 over infinity. All right. Okay, is it geometric? Nah, there's no n's in any powers. Is it harmonic? Well, we have the 1 over n, don't we? But we got a bunch of other crap down there too, don't we? So you can't split it apart. Remember, because that property, the question last class was, could you split this into 2? Could you do 1 over n times another 1 over natural log n squared? Can you do that? I answered that in the YouTube video. You can watch it. You cannot take the sum of a product and split it into the product of the sums. So that is not going to work. Even if it did, it would be harmonic times what the heck is that, right? What's the other one? So it looks like the only other method we know, the only other test we know is the integral test, right? So let's define our f of n to be equal to 1 over n natural log n squared. What are the things I need to check for? Okay, I'm going to first do continuity. Is it continuous? Yeah, well, that function's not defined at 0, right? You can't plug 0 in. You can't plug 1 in, can you? Check this out. What if you try and plug in? What if you plug in 1? What's natural log of 1? 0. You can't plug in 1. But what? What does my series starting index at? 2. So that avoided that. See that? So this is going to be good, right? This is good, yes, as long as I'm on the interval 2 to infinity. Very important. Next thing. Continuity. How about, is it positive? Is the function positive? Yeah, because 1 over n, let's see, natural log n squared, is that greater than 0? Yes? Yeah, because n is always positive, right? We're already saying n's going to be 2 and on. So that's positive. Natural log of positive number is positive. Squared positive. So this is all positive on the bottom. 1 over a positive number is positive. So that's good. So we have positive. Now the question is f decreasing? Which means I'm really asking the question, what? Is the derivative negative? Right? So now you get to do a derivative of that thing. So I'm going to look at it as quotient rule. All right? I'm going to do quotient rule. I think I'll do this right up here. The derivative of this function is the derivative of the top, which is, what's the derivative of 1? 0 times the bottom, which I don't even care, right? I just put a parentheses up there because that whole bottom's going to go away, isn't it? 0 times that. So that's going to cancel out. I don't even care. Then what? Quotient rule says minus the derivative of the bottom. What's the derivative of the bottom? And you know what? I'm going to run out of room up there. I'll do it down here. It's going to be a product rule here, right? On the bottom, you have product right there. And then that second product, the second factor is a chain rule. This is going to be a bit of a derivative, but we can get it. Here we go. So the derivative, again, was derivative top, which was 0 times the bottom. I'll go ahead and write it out now that I have a little more room. Minus, now I'm going to do a bracket here, derivative of the bottom. Can you all help me with this? Do that product rule. Well, what's the derivative of n? 1 times the second one, natural log n squared, plus what's the derivative of natural log n squared? 2 natural log n times, what's now the derivative of natural log n? 1 over n. And then finish off the product rule, then times the first function, which is n. Right? All of this over what? Quotient rule. Finish off quotient rule. The denominator, all of that squared. So that is your derivative of your function. We already said that this 0 kills that off. Over inside that bracket, the 1 over n and the n cancel. So what am I left with? On top, what do we have? Negative ln n squared. Careful. Minus 2 ln n. Yes? All over. Check this out. A positive number. Right? Isn't the denominator always positive? Because I'm going to square it. It's never going to be 0 because remember we're starting at 2 and on. So tell me about this. Is this negative or not? Well, natural log of n that